Welcome to the Deep Dive, your shortcut to being genuinely well-informed. Today we're getting into um, a really fascinating stack of research. It's centered on this MIT study that kind of upends a big assumption we all have.
Right, the assumption that there's this huge, clear line between, human thinking and machine computation.
Exactly.
And this research, it's mainly from Evelina Fedorenko's lab, published in PNAS, and it's a big deal. The main findings suggest that humans and these new reasoning-focused AIs,
The ones built to actually think.
yes, they seem to spend a comparable amount of, let's call it internal effort when they're tackling really tough problems.
That is just, it's astonishing to me. We all get the cost of thinking, right? Is there that feeling after you do your taxes or solve some awful logic puzzle, you're just drained.
Mm.
But the idea that machine, a language model, pays a similar measurable cost, it sounds like something out of a movie.
It really does, or it sounds like convergence. So our mission today is to break down how these researchers, especially Andrea Grigor-Devarda, actually measured this.
How they quantified it.
Right. Using two totally different yardsticks time for us and this thing called tokens for the AI. And maybe more importantly, what this accidental parallel means for how we think about intelligence itself.
Okay, let's start with the models.
Yeah.
Because this whole study, this comparison,
Mm.
it wouldn't have even been possible a few years back.
Not at all.
We all remember the first wave of LLMs,
Yeah.
right?
Yeah.
Ones that could just instantly spit out an essay or a summary.
And they were amazing, but they were prediction engines, really. They were just, incredibly good at guessing the next word.
Which made them fluent.
Super fluent, but they would just fall apart with logic problems or math or any kind of real step-by-step planning. They were brilliant parrots, not thinkers.
And that's the pivot. The sources we have really dig into this new generation of models, the ones built to fix that exact weakness.
Exactly. They weren't built for speed anymore. They were built for accuracy, for deep reasoning.
So what changed?
The big aha moment for the engineers was that the models needed a kind of an internal workspace.
Yeah.
As Devarda puts it, the performance got way, way stronger when they were designed to break problems down into smaller pieces and, work through them one by one.
So it's not about just giving one final answer.
No, it's about generating a chain of internal steps, a thought process.
So how do you train a machine to be thoughtful, to not just jump to a conclusion?
That's where reinforcement learning comes in, RLHF. You hear that a lot. Reinforcement learning from human feedback. So instead of just predicting the next word, the model tries out different internal pathways, different steps to solve a problem.
Okay, so it's like a self-critique loop.
That's a perfect way to put it. It tries a path, and if the final answer is right, that sequence of steps gets a reward,
And if it's wrong, a penalty.
a penalty. And you do that millions of times, and the model learns the best, most efficient internal sequence to solve something complex.
So they take longer?
They take longer, but they are so much better at things like writing complex code or solving university-level math. It's a trade-off.
That trade-off speed for depth is so interesting. And it really sets up the whole comparison, doesn't it? If AIs are now designed to take their time to reason, you have to ask, how does that machine effort compare to our effort?
And that takes us right to the heart of the MIT study. How do you measure the cost of thinking in two completely different systems?
Well, I assume they started by giving them the same test.
They did. Both the human subjects and the AI models got the same set of tasks. Some basic arithmetic, logic puzzles,
Sure.
and the big one, the abstract reasoning challenge or the ARC challenge.
Right, the ARC challenge. For anyone who hasn't heard of it, explain why it's such a beast. Why is it so hard?
It's hard because you can't use language or memorized facts from the internet. It's pure fluid intelligence.
It's all patterns.
All patterns. You're shown a few examples of a grid of colored squares being transformed into another grid, like input A becomes output A, and you have to figure out the rule. Is it a rotation, a color change? And then apply that rule to a new input grid,
It forces you to generalize from just a few examples.
which is incredibly hard for humans,
Yeah.
and it turns out even harder for AIs.
Okay, so the test is identical. The landscape of complexity is the same for both. For the humans, measuring effort is pretty straightforward, right? It's just time.
Exactly. The more time you spend staring at the screen, struggling, the more cognitive effort you're using. It's a great proxy.
But time is useless for an AI.
Completely useless. A supercomputer can solve something way faster than a laptop, but that doesn't mean the problem was easier for it. It just has better hardware.
So they needed the AI version of time spent struggling.
Yep. And that's where they landed on counting the internal tokens.
Okay, Let's break that down because it's the key.
Good.
What is an internal token?
So we usually think of tokens as the words the AI spits out for us to read, but these are different. These are the invisible bits of computation the model generates while it's thinking. DeVarda describes it as the model having this sort of internal monologue, a private scratch pad where it's working out the steps.
The great analogy, a scratch pad. But wait a minute. How do you know that a high token count means real effort and not just, the model generating a bunch of useless garbage on its way to the answer?
That's the million-dollar question. And the answer is in the correlation. If it were just random, wasteful processing, you'd expect the relationship between human time and machine tokens to be all over the place, a total mess.
But it wasn't.
It wasn't. It was an almost perfect one-to-one relationship.
So lay out the headline finding again for us.
The problems that took humans the longest time, the ones that really caused that mental strain, those were the exact same problems that forced the AI to generate the most internal tokens.
And the easy problems for us were easy for it.
Minimal token count, a breeze, and the ARC challenge.
The absolute peak for both. The hardest task.
The hardest for both. It demanded the most time from people and the biggest computational load from the AI. This really tight parallel suggests that the inherent complexity of a problem demands a similar amount of processing work, no matter if you're a brain or a circuit board.
And this is where it gets really wild for me. This whole thing.
Right.
This convergence.
Yeah.
It wasn't on purpose.
Not at all. That's the biggest surprise. Fedorenko says it herself in the research. The people building these models, they don't care if it works like a human brain. They just want it to get the right answer. Robust performance is the goal.
So the fact that the best way to get that performance also happens to mirror our own cognitive cost.
It's, and I quote, really quite striking. It suggests there might be, some kind of universal rules for how intelligence has to work.
It's like two people trying to climb a mountain from opposite sides with no map. And they both discover that the only way up involves taking the exact same number of steps.
That's a perfect analogy.
Right.
And this is a huge, the researchers stress, we have to be careful here.
Right. Shared effort does not mean shared thought.
Precisely. They are not saying these models are digital brains.
So what's the difference then? If they're paying the same cost, what's happening under the hood that's so different?
Well, the internal representations could be completely alien to us. We have neurons, we have, a lifetime of physical experience in the world. The AI has matrix mathematics. So the big questions are still there. Does it really understand these concepts? Can it generalize in the same way we do?
Let's go back to that internal scratch pad, the monologue of tokens. Is the AI actually thinking in a human-like language?
This is another fascinating piece. DeVarda points out that if you actually look at that raw internal stream of tokens...
The scratch pad?
Yeah, the scratch pad. It's often full of errors, logical mistakes, weird, nonsensical bits, as they put it. And this is happening even when the model gets the final answer perfectly correct.
Hold on. So the internal process is messy and flawed, but the final output is clean and right.
Exactly, which argues pretty strongly that the real deep reasoning is not happening in that language-like stream.
The language is just a shadow of the real work.
Yes. The source suggests the heavy lifting, the actual computation, is happening in some abstract, non-linguistic space. The text is just a translation of that deeper process.
Which is eerily similar to how people describe thinking. I mean, when you're solving a hard physics problem, you're not reciting sentences in your head. You're manipulating abstract concepts, images, formulas.
The language only comes when you try to explain it to someone else. It's this incredible parallel. Both systems seem to use language for output, for bookkeeping, but the real abstract thought is happening somewhere deeper.
So we have these machines, they're optimized for nothing but performance. And in doing that, they accidentally discover the same effort-based rules that biology gave us. What does that mean for the bigger picture, for intelligence itself?
I think it really marks a turning point. We're watching AI move from just being a fancy prediction tool to a system that can do real, structured, and costly reasoning. And that unintentional convergence, it suggests there are some requirements for problem solving that might be, fundamental.
Fundamental to the problem, not the thinker.
Yes, regardless of whether the thinker is made of cells or silicon.
You're saying complexity itself has rules.
That's the big implication. To solve a truly hard problem, any system, human or AI, has to pay a high computational price. You can't just cheat your way around it.
It just opens up such a huge door for, collaboration between neuroscience and AI.
Absolutely.
If the AI is converging on our methods, then Maybe studying the machine's bottlenecks, where it generates the most tokens,
Mm.
could give us clues about our own cognitive bottlenecks.
It changes the whole conversation. It
Yeah.
shifts the definition of intelligence away from just speed and toward the actual measurable work of thinking. It gives us a universal benchmark for the cost of a thought.
Wow. This accidental discovery, finding this common ground between our time and the machine's tokens, it really does feel monumental.
It is. It suggests there might be these universal, unavoidable laws of computation that govern any intelligent system.
The hardest problems just cost more, period.
Exactly. It's like there's a universal ceiling on efficiency that's imposed by the structure of complexity itself.
Hmm.
All intelligent systems have to play by the same rules of effort to get the job done right.
Which leaves us with a final provocative thought for you to take away. If a machine's hardest thoughts cost the most tokens, does that mean the complexity itself carries a universal price tag for wisdom? What hidden cost in time and in internal energy are you paying right now for your own most difficult, non-linguistic thoughts? Is that effort ceiling truly unavoidable?
Something to think about next time you're just staring at a problem.
Thank you for joining us for this deep dive. We'll see you next time.